Okay, let's begin. For it is the first time I try to speak English in physics seminar, I decided to discuss only half of what I have prepared as usual, which means it will take only about 40 minutes to give today's seminar. If the effect is good, I will move the lab's content to next Saturday. And one another thing, we will meet some difficult words in pure English seminar, but I will not speak Chinese to explain them. I will use simple English to do that. Today we will talk about something of formalism. First, let's go through what we have discussed in former seminars. We have discussed the two principles of quantum mechanics, superposition and indeterminacy. After that, we defined wave function and discussed its property, especially the duality property. And then we defined operator and its matrix so as to obtain some useful conclusion. In the end of last time, we introduced Dirac's notation. Okay, I will write it again. Consider an operator f and write its matrix like f, k, j. We have known that it can be written as an integral form like k psi j dq. Now we introduce Dirac's notation as an equal form to the left matrix. We can write it as Dirac k f kit j. Okay. Now there's a question. Can we make a formal mathematical scheme, or we say a formalism, to describe all above theories? The answer to this question is absolutely yes. We have mentioned over and over again the significance of the algebra structure beyond all above theories. So we can confirmly make a formalism, just as what algebra does. Now let's follow Dirac's textbooks to construct the formalism step by step. The first problem we must face to is that how to construct a formalism. Let's go through what we have learned in linear algebra. First, we assumed some axioms of adding and multiplying. After that, we define linear space and linear transformation and so on. So in quantum mechanics, we can follow the same method. First, we use two principles of quantum mechanics, and then we infer axioms. After that, we define space and operator. Okay, since we have mentioned the two principles, it is more reasonable for to construct the whole scheme to consider superposition and indeterminacy from an experimental example, the polarization of photons. Of photons. Let's suppose a beam of plane polarized light. A beam of plane polarized light. Okay, I will draw it again. And make it pass through a polarizing field. Oh no. A polarizing film. Okay, the film has its own direction. Oh, and there is the backside. So, let's consider the two extreme cases first. When the beam of the light is polarized perpendicular to the direction of the film, okay, when we say perpendicular, when we say perpendicular, if we say A is perpendicular to B, we say A is perpendicular to B. Okay, perpendicular. And in this case, we know, when the light is polarized perpendicular to the direction, we will know that none of it will pass through. Okay. And in the other extreme cases, when the light is polarized parallel to the direction of the film, just like this, parallel. Okay, parallel means when we say A parallel to B, it means A parallel to B. Parallel. Oh no, parallel. We mean that. Okay. And in this case, we can see the whole beam will pass through. Okay, let's consider about the general cases. General cases. If the beam of light is polarized at an angle alpha to the direction of the film, angle alpha to the direction of the film. Now we will see a fraction cosine square alpha of the beam will pass through. That is what we have learned in optics. Now let's consider it in another basis. How can we describe it on a photon basis? Okay, that's important. According to the photoelectric effect, we will know that if a light beam consisting of photons is plane polarized in some direction, then we know each of the photons is polarized in that direction as well. Okay, that's what we could obtain from photoelectric effect experiment. Okay, let's consider about let's consider the extreme cases first. It will be easy for if a beam of light is polarized perpendicular to the direction, we know that each of the photons is polarized perpendicular to the direction, and so none of it will pass through. And in the same way, we can consider the cases that the light is polarized parallel to the direction. But when we come to the general cases, a problem will arise. Difficult problem will arise, because if we suppose the light is polarized at an angle alpha to the direction, now we will see that each of the photons is polarized at an angle alpha to the direction. But when we take a single one, we don't know what will happen when it comes to when it reaches the film. We don't know what will happen. So that's a problem that we can solve in classical scheme, and the only way to explain that is to suppose that the general cases is a strange state, that each photon is in the strange state that partly in the state of perpendicular to the direction, while partly in the state of parallel to the direction. Partly perpendicular, while partly parallel for a single one. Okay, so when we observe the back side, we will see sometimes we will observe the whole photon, while sometimes we will see nothing. If we repeat the experiment in a large numbers of time, we will find that a fraction cosine square alpha of total times we will see a whole photons in the backside. And so in other words, we can only obtain the probability of the photons. And we call that indeterminacy. And we say, and we can define. Yes, we call the strange states is superposed by the two states. Superposed. Oh no, superposed. By two states. And we call that the superposition of states. Superposition. Superposition.